SwayamPrabha. Digital India. Educated India.
Hello and welcome to the first lab session of the course. We are in the Technical Art Laboratory of the Mechanical Engineering Department of IIT Kanpur. This is the lab where we impart the hands-on training to the second year students, irrespective of their disciplines and the departments. So, all the students of the institute, which is now about 1000 students, they go through this lab every semester. In this lab, we have a series of turning machines. These are the conventional turning lathes. We have a series of milling machines, series of turning, as I said, then the drilling machines. We have the tool grinder. Apart from that, we have a series of computer numerical controlled machines that we will go to, and we will have a demonstration as well. So, the students also go through a project, and in the project they actually apply the experience that they go through, which they have been taught, which they have been given as an hands-on experience by the very experienced technical personnel in the lab. We have about 18 technical personnel in the lab. They are highly qualified and they guide the students, help the students in their projects. So, we will as well share this experience with you. That is the intention of the lab session of this course. Now, this lab session will be divided into basically two sections. One will be for the conventional machines. There we will have exercises on turning, on drilling, on milling, on the tool grinder, and the second part will be on the computer numerical control machines. There you will be shown how to program the parts in the turning and in the milling, and then how to implement them. I mean, how to execute those programs to make the parts in the turning CNC machine or in the milling CNC machine. Altogether, we are planning for about 10 hours for this lab session, and of course 10 hours for the lecture session. So, let us have a overall look of the lab, and then we will come back to the turning machine. We will start with the lathe, and then we will go about serially as milling, then after that we will go to the drilling machine and so on. Well, you can see in the TA 202 lab, this is the technical art lab. This is the tool store that you can see, from where the tools are being issued to the students. Those who go through the laboratory exercises. Here you can see the vices. These are the drilling and fitting section. So, they learn how to drill manually, how to tap manually, how to file, what are the different kind of files and so on. There you can see the cutting section. There we have the blanks from where they cut into pieces for making the shafts, for making the gears, etc. And there in front of you, you can see the drilling machines. Those are the vertical drilling machines. And at the far end, you can see the shearing machine, and over there, there are 2-3 shearing machines there, and you can see the vertical drilling machines all over. There are about 6 to 7 vertical drilling machines, and on each drilling machines, the students actually themselves they use it, and they drill the holes for the parts that they are using for their projects. So, as I was telling you that about 100 plus students of the second year of IIT Kanpur irrespective of their disciplines, they go through the laboratory works in this laboratory, and they are given hands-on training by our highly reputed about 18 technical personnel. Now, we also take the precaution. This is for the safety of the students. We give them apron, we give them the glasses, we give them the gloves, and it is mandatory for the students to come to the lab and carry out the experiments using the shoes and the full sleeve shirts without any loose shirts. For the girls, it is mandatory to have the hair tied up at the back and so on. So, all those are the precautionary measures that we take. Now, the students also go through the projects, they do the projects, and some of the projects I would like to demonstrate. For example, this is one project which is the grass cutter, and the entire thing is designed by the students, and it is fabricated by the students with the help of the technical personnel. Now, in here, as you can see that the grass will be fed here. These are the parts which the students have made using the 3D printer, or which is the rapid prototyping, which is called nowadays as 3D printer. We have few 3D printers here also, and the students are given the knowledge of operating them and making the program and making these kind of parts. For example, this is the plastic part which is a clamp that you can see, which is the clamp for the motor, and these are the supports for the grass. All right. So, the grass will come here and it will actually be driven by the motor, and the grass will be cut from here. This is the cutter. So, this is a small project. For example, here if you see, this is a spirograph, and this is also made by the designed and fabricated by the students. And here if you actually put the power on, then you can see that there will be movement, relative movement between the the pencil and the table, and you can see that there are different kind of patterns that can be drawn, and depending on where you are putting the pencil, that pattern can be changed. So, you can see the pattern that has been made here, and as I said, I repeat once again that the entire design is made by the students, and all the parts are being fabricated by the students. So, while fabricating, while designing, the students also are implementing the design knowledge, the fabrication knowledge, and so on. So, you can see some of the more students projects. This, for example, is the rope making machine, and there we have the mechanical arm. So, these kind of projects are made by the students in a group of about 6 to 7 students, and they design the entire thing, then they fabricate the gears, for example, the spar gear, bevel gear, and they also assemble the same thing. So, this is another project which is the mixer basically, and you can change the velocity. As you can see that this is a simple mechanism which actually is designed by the students and fabricated by the students as well. Here if you see that this is the peanut crusher, also a very simple design. Here the peanuts with the cover, it comes here and they are being crushed here, and it is segregated. The outer shell will be segregated because they are by the fan, because they are lighter, and the peanuts will be collected. So, here also it is manually operated, it can be operated like that. So, as you can see that this is the design which will actually crush the peanut and segregate the seeds from the shells, and then the shells will be segregated there, and the peels, the brown peels will be coming from here. They will be segregated overall. So, that everything will be separately collected, and this works very effectively, also designed by the students. Well, this is the turning machine, which is as you know, known as the lathe machine. So, here we can make the cylindrical jobs. We can make the taper surface, we can make the internal hole as well, and then we can also make the flat surfaces. So, here what you see is, for example, in this machine we have the 3-jaw chuck, and this is for clamping the workpiece. So, basically the 3-jaw chuck is used for clamping the cylindrical piece, where you have the center of the cylinder which will be coaxial with the center of the 3-jaw chuck, and apart from the 3-jaw chuck we also have the 4-jaw chuck that we will be showing you a little later. Now, this here is the spindle. The chuck is on the spindle of the machine. This spindle is held by the headstock, and the spindle is given different RPM, revolution per minute, or the speed, all right, rotational frequency, with the help of the headstock. Now, here we have the tool post and the for clamping the tool. Now, this tool post can be given 2 feeds, and as you know that the feed is the revolution per minute, that is the millimeter per minute. That means how much the tool will be moving along the axis in case of turning along the axis of the workpiece in millimeter per 1 revolution of the workpiece. All right. Now, here the tool will be clamped. These are all the turning tools, single point cutting tools. So, the rotation of the spindle, this is the, since the workpiece will be clamped here. So, this will be the cutting speed. Now, of course, as I said, the rotational frequency is given to the spindle, and depending on the diameter that will be fixed here, diameter of the job, pi, d, and the n is the revolution RPM. So, that will define the cutting speed. Now, the feed motion is given to the tool which is clamped here in the tool post, and as I said that the feed is given in millimeter per revolution. That means, the movement of the tool in millimeter per 1 revolution of the workpiece. Now, depending on the rotation and the feed given to the tool, there will be different kind of surfaces. So, the surfaces can be cylindrical surface, then it can be the taper surface, it can be internal cylinder, it can be. So, everything will depend on the relative movement between the tool and the workpiece. For example, if the workpiece is rotating and the tool is given movement of the feed which is parallel to the workpiece axis, then as you know that we will be getting a cylindrical surface, which will be external cylindrical surface. And if the feed given to the tool is not parallel to the workpiece surface, it is inclined to the axis of the workpiece, then we can get either an internal cylindrical surface or an external cylindrical surface. Now, the difference is that while we are getting the external cylindrical surface with the help of the tool which is mounted on the tool post, for the external cylindrical grinding, for internal cylindrical grinding, we have to have a boring tool. So, the boring tool will be fixed at the tailstock. All right. So, the tailstock is used to fit the boring tool or the drill, or also it is used to support the very long workpieces which will be mounted on the spindle with the help of the 3-jaw chuck, or very long pieces like rods, for example, okay, which needs a additional support because they are flexible, they are not very rigid. So, in that case it will be supported by different kind of mechanisms. We will be showing it to you. These are the rests also that will be mounted in the tailstock. So, we have the headstock once again, we have the tailstock tool post, and the tool post is mounted on the lathe bed. All right. So, the lathe bed is here, as you can see that these are the, as you know that these are the dovetail and this is the flat. So, okay. So, this is for the tool post to move, all right, to and fro when the feed is given to the tool. Now, apart from the longitudinal feed, which is the feed given to the tool along the axis of the workpiece. We can also give the feed to the tool perpendicular to the axis, that means in the feed direction. All right. So, this can be given, this is the feed that is given manually, which is the longitudinal feed that is parallel to the workpiece surface, and this is the feed which is the the correction which is given to the feed direction. All right. This will be the longitudinal feed and this will be the axial feed. So, this is in the this feed when it is given to the tool, axial feed. So, this feed will make the flat surface, meaning for example, when the facing is done, all right, or parting off is done, then this feed is given, that is perpendicular to the workpiece surface, and this feed is given for the making the cylindrical surface, external cylindrical surface. Right. So, this that you see here is the lead screw, and the pitch of the lead screw defines how much the tool will be moving, the tool post will be moving with the when you are actually putting this, rotating this wheel. And this is the handle which will help, as I said, to switch on and switch off the machine, and below that there is an emergency brake, and that emergency brake is used to stop the machine immediately, because with this handle the machine still will have some sort of inertia and it will not be able to be stopped immediately. This shaft that you can see, this is used for feed, this is called the feed screw, and here is the lathe bed, as I said earlier also, that this is the dovetail cross section, and this here we have the flat cross section. So, with the help of the dovetail and the cross, the lathe bed will support the tool post as well as the tailstock, and once again the tailstock will have the support for the long rods or the work pieces which are clamped between the centers. So, the dead center and the live centers will be mounted in the tailstock, that will be for supporting the work pieces. So, as I was telling that this is the headstock, and inside that we have the gear train, gear mechanism, and the gear train defines the rotational frequency of the spindle and the workpiece which is mounted on the spindle. These are the handles which will define different kind of revolution per minute given to the spindle. For example, in this case here there are tables, as you can see. So, for the spindle RPM, if it is this handle is in this position, okay. So, this is the 112 and A, it has to be then A. If it is given in the B, so B means here, so it will be in this position. Okay. So, this will be 710. So, if you have to shift from 112 to 710, you have to simply shift from here to here. So, this will give you the second value, and here this has to be in the A. So, it is in the M. M has two values of the spindle speed, 112 and 710. So, either it is 112 if it is in the A and the A and M position, or B and the M position will give you 710. Anyway, this is not so important because this is only pertaining to this particular machine. In another machine, the arrangement can be different. All right. So, overall what I am saying is that you can get different kind of spindle speeds RPM with the help of this. So, there are 8 spindle speeds that you can get, starting from the 71 up to 1800, because these are not the so modern machines. So, therefore, here it is only up to 1800 RPM that you can get, and therefore, high speed machining cannot be performed in these machines, because the RPM cannot be taken more than 1800. And similarly, we have another table which is used for the feed and the pitch of the thread that you can cut. So, you can also get the threaded surface as you know, that is using the turning. So, here there will be a threaded tool, thread cutting tool, particularly in the tool post, and that thread cutting tool will show you how to cut the thread and how to operate the machine, how to get the spindle speeds and so on. So, you can see the inside of the gearbox, which is attached to the headstock of the machine. Here we have the main drive, and the power of the main drive, as you know, has to be little more than the power that is required for the cutting, so that there is no slip. Now, from the main drive through the belt and pulley system that you can see here, that this is the driver pulley and this is the driven pulley. Here we have the flat belts, there are 3 belts here, and this is transmitted to the pulley here, and this pulley on the shaft of this pulley inside the headstock, it is given, the transmission is given from there through the gear drive to the driver gear here. All right. So, from the driver gear through the gear transmission, as you can see from here, and it goes and it is attached to another gear here. From here, because this gear is on the same shaft as the gear inside, which is attached to this gear. So, this will be rotating, and in its turn this rotation is imparted to this shaft through the gear here, and that gear is sitting on the shaft, which is going inside the gearbox. Now, in this display board, you can see the tools. These are the turning tools, drilling tools, and the measuring instruments that are used for measuring the diameters, lengths, etc. So, we will discuss about the tools and the measuring instruments in details in the lecture hours, but here I would like to show you some of them. For example, this is digital micrometer, and digital micrometer because you can actually find out the value which will be displayed here digitally. Also, you can measure the value from the scale. This is the linear scale and this is the vernier scale. So, using that you can find out the diameter, for example, diameter of this cylindrical surface. So, this can be placed here and the diameter will be displayed, the diameter of this cylindrical surface will be displayed here. Also, you can find out from here, let us say, that is, this is the outer scale and this is the vernier scale. So, from here you can find out what is the diameter of this. Or for example, you can also find out the thickness. Let us say you want to find out the thickness of this scale. So, that can be found out. It has to be held in between the 2 jaws, and the thickness of this will be displayed here. All right. They are quite accurate. Similarly, we have inside micrometer. So, inside micrometer, as you know, that if you have to find out the inside diameter of a cylindrical hole, so this will be put inside this hole. Can I get a hole here? And then you can actually fit this 2 jaws inside the hole, and you can measure the diameter through the scale. This is one scale and this is the vernier scale. So, the bigger scale will be the value, and the decimals will be found out from the vernier scale. All right. The details of the vernier scale and how to read the vernier scale, that we will be discussing in the lecture class when we will discuss the measurement. So, let us say you have a nut and you have to find out the internal diameter or the diameter of this nut. So, you can fit in this the external jaws inside, all right, like this. So, here, and then you can find out the internal diameter of this nut through the scale which is here. So, as you can see that this is about 25, it is almost let us say 20 something, Okay. So, that is something you can find out, that is the decimal you can find out from the vernier scale, that we will be discussing in details in the measurement course, metrology course. Here you can see that this is the outside micrometer. Outside micrometer is very similar to the one that we have shown here. This is the digital, where it can be displayed here. Also you can measure, by the way, and this is, there is no digital display. Here you can find out you have to find out the measurement from the scale that is here, that is the linear scale, outer scale, and the vernier scale. All right. Now, here this is the bevel protector. This is used for measuring the angles, and here you can see that this is the lens through which you can find out the value. This is rotating, and this is the vernier one. There is one, as you can see from this, through this lens you can see the vernier scale as well as the main scale. So, from here you can find out what is the value of the angle that you are measuring. Here we have the digital vernier caliper, and the digital vernier caliper with respect to any hole, either it is an internal or the diameter, if it is an diameter of a shaft, or it is the internal diameter of a hole. So, that also can be found out from these jaws, and from these jaws you can find out what is the external diameter of a shaft, and this will be displayed in this, this will be displayed digitally. For example, this gap, the value of this gap is displayed here as 238.44. Okay. So, it will be in some unit, that unit can be fixed here, okay, and you have to set the 0 and so on, of course. Yeah, all right. So, if you set the 0 and then if you take it out, so it will be, for example, right now what it is showing is 17.85. So, this is the gap which is shown as the 17.85, probably this is in millimeter, it is given in millimeter. All right. So, it is useful, and it is quite convenient, because you do not have to read in that case the scale and the main scale and the vernier scale, and you can find out what is the value. So, here it is the vernier with the dial indicator. So, instead of the display you can also have the dial indicator, where you can directly find out from the dial indicator what is the value of the this thing. This is for the diameter of a shaft, and this is for the internal hole, that is diameter of the internal hole. That means, within the hole, that the same thing you are putting it inside the hole, all right, and you are finding out what is the value of this diameter from the dial indicator. So, this is the same principle as in here, only thing is that here it is displayed, and here it is given the read through the dial indicator, but the principle used is the same. This is a very popular, as you know, that this is the manual vernier caliper. There is no difference between these two, only thing is that this has a dial indicator, and here you have to manually find out the read the value. So, the value that you can read is again the diameter or the distance between the two surfaces, for example, like that, or if you have to find out the diameter of an internal hole. So, there these two jaws can be used, and again then you have to find out the value by reading the main scale and the vernier scale. As I said, that this we will be discussing in the metrology class in details, that how this can be read, and you know that there is a list count, concept of list count in the vernier. That list count, how to find out, how to measure, that we will be discussing in the metrology class. Next, that we have, of course, a stainless steel scale that you know. Then we have the thread gauge, and the thread gauge is useful because in that case you have to just match one of them in the thread, and you can find out each one has the value written on this, and you can find out what is the value of the pitch. For example, in here you just match what is the thread, where it is, which one is matching here. There are two sets of that, okay, and accordingly you can find out the value. The values will be written here on each of them. All right. This is the fishtail gauge. Here you can find out for the bigger threads, all right, what will be the pitch or what will be the angle between the two sides of the thread. Okay. We will show it during the machining how these angles can be found out. This one, as you can see, this is called the knurling tools, and there are different kind of knurling that are there in the tool, all right. And we will have a turning operation. There we will be using this knurling tool to show you how the knurling surfaces can be obtained. And as you know, the knurling surfaces are obtained to get the, let us say an example is this, all right. Example is this. So, this is a knurled surface, as you can see. So, this is for gripping, for well gripping, okay. And also in very fine knurling is used in the in different objects to retain the lubrication, okay. When particularly the two objects are meeting each other and they are knurled very finely, in that case the knurled surface will retain the, let us say, solid lubricant or the liquid lubricant as well. So, this is the process which is called the knurling, and the tool is called the knurling tool, all right. This is the tool which is called the carbide tip boring tool. Carbide tip is because this tip only is made of the carbide, okay. It can be tungsten carbide or silicon carbide, all right. So, these carbides, the tool material, when we will discuss the tool material in the lecture class, we will tell you what these carbides are for and why these carbide tips are used in the tool. So, let me discuss a tool with you. So, this is a tool which is the single point turning tool, and this is called the left hand turning tool. Somehow we have the left hand turning tool as well as the right hand turning tool. So, these are the turning tools which are used for used on the lathe, okay, to get the cylindrical surfaces on the lathe machine. So, in this, here we have basically the 6 angles, okay, and the two main surfaces, one surface is the rake surface and another surface is the flank face or flank surface, all right. Now, the angles that the tool must have, these are the rake angles, the flank angles, okay, and the cutting edge angles. So, those angles in details we will discuss in the theory class, but you can see here, for example, in this tool there are different inclinations. One inclination you can get on the rake face, one inclination which is different from this will be on the flank face, and another inclination which is different from the flank face as well as the rake face is the side. Okay. So, as you can see that there are 3 faces with 3 different inclinations. So, therefore, there will be 6 angles altogether, 3 sets of angles, 1 set of 2 rake angles, 1 set of 2 flank angles and 1 set of 2 side cutting edge angles, all right. So, those 6 angles together will define the entire tool, which is the single point cutting tool, or sometimes it is called the turning tool or lathe tool, in different ways they are called. So, we have the left hand tool or the right hand tool. Here is the right hand tool, principle is the same, but depending on how this is shaped, all right, either in the left or in the right. So, this is called the right hand turning tool or the left hand turning tool. Well, there are also different tools. For example, here you can see that this tip is different from the one that you have shown, you have seen there, and that is called the radius profile tool. That means, if you have to make a profile the same way as the profile shown here, then this tool can be used with a cross feed. The feed then can be given towards the axis, that is perpendicular to the axis. In that case, what you will be getting is the groove which will have a radius of the same value which this tool is having. So, this kind of tools are used for that purpose, for the profile cutting. Now, here you can see a tool which is actually used for making the internal threading. So, this is the threading tool, all right, and that threading tool will be clamped on the tool post, and this will go inside the workpiece in this way, and the workpiece will be rotating, all right. So, we will show you some in the thread cutting, but mind it that this is for the internal thread cutting and this is the tool for the external thread cutting. Okay. So, external thread, of course, it will be held on the on the tool post, and it will touch the external surface, cylindrical surface, all right, and the feed will be given parallel to the workpiece in both cases, either it is an internal thread making or it is an external thread making, all right. Now, of course, here also we have to maintain the angles, and those angles will be little different than the left hand or the right hand tools. Here the most important angle is the angle which is given by these two surfaces. Okay. So, this is the thread angle that is important in this case. This is the tool holder, all right, and in this we have a tip which is used for the cutting tool, all right. So, instead of, for example, if you see this, the entire thing is of one material, okay, single material, either it is a high speed steel or any other steel which by which this tool is made. Here, not to waste so much material, because the tool material is costlier, we will discuss it later. So, only the tip is made of that material, tool material, and that tip is attached to the tool, as you can see that this can be loosened and this tip can be taken out, another tip can be inserted when this tip will be worn out, all right. So, this is the holder that can be used multiple times, all right. Even if the tool tip is broken, in that case another tip can be inserted here, all right. So, this is called the inserted tool tip, okay, inserted tip tool. Here this is a drill, okay, which is used in the drilling machine to drill the hole, or it can also be used in the turning lathe for drilling an internal hole, all right, in a cylindrical surface. So, I was telling you there during the when we were describing the turning lathe, that in that case the drill has to be mounted in the tailstock. Drill does not rotate in that case, all right. It will be fed towards the workpiece, all right, parallel to the workpiece surface, and the workpiece will be rotating. Workpiece will be clamped in the 3-jaw chuck or in the spindle by the 3-jaw chuck mostly, because it is a rotating workpiece. And in that case the internal hole will be produced, internal hole will be fabricated. This is the tool which is the in that case is a drill. Now, here also you can find out another drill, but the difference, as you can see, that this is the taper surface and this is the cylindrical surface, all right. Meaning that if the diameter of the drill is more than 10 to 15 millimeter of this drill diameter, in that case you have to use the drill with a taper shank. This is called the shank, which will be fitted in the drill chuck. Okay. The drill chuck is here, this is called the drill sleeve, all right. So, it goes in here and it sits, all right. So, this will transmit through the taper surface of this chuck or of the drill sleeve the torque given to the tool. In this case, this is the drill, all right. So, as I was telling that there are two things, one is the cylindrical, two surfaces, one is the cylindrical surface, another is the taper surface. So, cylindrical surfaces are used, cylindrical surface of the shank is used when the tool is of smaller diameter, let us say around 10-15 millimeter, and more than that it has to be a taper, because the torque carrying capacity has to be more. In this case, torque carrying capacity is less than the torque carrying capacity of the drill with the higher diameter. So, it will be fitted here, all right. And this is the taper which is called the Morse taper. So, where it is fitting in the drill sleeve, the internal taper hole should also be fitting with this in this. So, therefore, it also has to be the Morse taper, and when it goes in, it actually fits in, that is it. You have to then take it out very, using large force. For example, if you put it here, it will actually stay. So, this will be used in the tailstock for the turning lathe, and for the drilling machine it has to be used in the using a special kind of a chuck, similar type, all right. Now, here what you see is a window, all right, and the drill, this is called the tang, drill tang, T-A-N-G. So, this tang is particularly given so that the drill can be taken out. As I was telling, that if you put the drill here, the two Morse tapers, one which is outside the shank and one which is inside the shank, those two will fit very tightly, all right. Because as you can see that when this will be rotating through the taper, the torque will be transmitted to the drill. So, therefore, there should not be any relative movement between the drill chuck or the drill holder and the drill, otherwise it will slip. So, it should not be like this, there should not be any relative movement, it should move together, all right. So, therefore, it will sit very tightly and it is difficult to take out the drill many times. So, there is one wedge shaped tool that is called the drift, all right. This is called the drift, this is driven here, since it is the wedge, okay. So, if you hammer it from here, this will be coming out, all right. So, this is called the drift or the wedge, and this is taken, this is used for taking out the drill from the drill chuck, and this is the tang. Mind it, this is not used for transmitting the torque, this is used to just remove the drill from the drill holder or the drill chuck here, all right, and using the wedge shape tool like that. So, that problem will not come here, because in this case we have a cylindrical surface, and this is simply, it is actually held and the torque is transmitted with a different principle than the principle used here. Once again, I will repeat that the torque is transmitted through the spindle and the chuck with the help of the Morse taper only, all right. Among the other tools, here you can see that this is an adjustable spanner. So, adjustable because with the help of this screw, you can actually adjust the distance between the two jaws, so that the different diameter of cylinders can be held between the two jaws, all right. And it has a span of very wide span. This is the maximum diameter that you can measure, and the minimum diameter also accordingly. Here this is a spanner, this is a normal spanner, everybody must have seen them, and here you can actually put the nut, hold the nut and tighten or loosen the nut, all right, hexagonal, square, all right. So, these are the two different one, and here the number will be given. So, according to that you can actually select one of them, either it is 7, this is called standard, and this is the 5. So, these are the standard sizes, and there are different spanners, as you know that in a set of spanners you will have starting from 5, 6, 7 and all numbers you will find. So, this I have shown it to you that this is a drift, all right, and it is actually a wedge shaped part. This normally used for taking the drill from the out from the drill chuck. These are the keys which are called the Allen keys, and the Allen keys are used for tightening such kind of screws. Okay. Here if you see the head, in this head these Allen screws actually fit in well, and then you can rotate so that the screw can be put inside the threaded hole. So these are the Allen keys. They are of different sizes. This is bigger, this is smaller, all right. And this is the standard dial gauge, and this dial gauge is used for measuring the height, the out of roundness, out of cylindricity, and many other purposes. For many other purposes, this kind of dial gauges are used. So for that, you put it on a metallic surface. Then if you rotate this, there is an electromagnet. So that electromagnet actually will put this firmly, put the base firmly on the metallic surface, and then you can use the dial indicator for measuring with the help of this. You can lower that, or you can take the angle, change the angle, and so on. So as I said, that for different purposes such kind of dial gauges are used, and those dial gauges are of different least counts, meaning that what is the minimum size that you can measure using such kind of dial gauges. There are fine dial gauges, there are rough dial gauges. Fine dial gauges least count will be very less, let us say 0.01, 0.002, and so on. And for the rough dial gauges, you will have the higher least counts. These are the two parts which are called the centers. This is the revolving center, which actually revolving because it revolves along with the spindle or the tailstock, and this is the dead center which does not rotate, which is fixed. So these are the centers which are used for supporting the long shafts. I was telling you when describing the lathe functions that these are the two, between two of these centers the long rods can be supported, so that the entire length of the rod can be turned. Okay. And here normally this is kept in the spindle, this is kept in the tailstock, spindle in the headstock, this is the dead center in the tailstock normally. So between these two centers the cylindrical job can be held, and of course while giving the motion or the movement to the shaft, the other devices which are used, the dog carrier, that I will show you little later. So once again, this is the revolving center and this is the dead center. Between these two centers the long cylindrical jobs can be held. All right. For that, of course, in the long cylindrical job the center hole has to be made. Special center holes are made, as you know. So within that, those center holes, the centers are inserted and the shaft will be rotated between these two with the help of such. This is called the lathe dog or lathe carrier. This is the device which is actually in between. It goes in, the shaft goes in, it is, and the rotation is imparted with the help of that which is attached to the spindle. All right. We will show it to you how from the chuck the rotation can be imparted to the cylindrical shaft with the help of this dog carrier. Okay. This is a marking block. This marking block is very simple. This is used for marking the plates where you have the center, or you have the center hole, or you have the other margins. So these are the pins, okay, and these are used for marking the block. Of course, the material of this has to be hard so that it can scratch, okay, the other material, and should not wear out, because these are very sharp pins. This is a drill chuck, and this drill chuck, I have already told you that, as you can see, that there is a Morse taper, okay, similar to other one that I have shown it to you. So this is the one that I have shown it to you earlier. So in this drill the diameter of the drill is higher. So, therefore, you have a more taper shank. Similarly, here also you will have a taper shank, and this taper is also a more taper along with the tang here. This tang is once again to take out the entire drill chuck from the drill holder from the chuck of the drill. So, here if you see the drills that are normally of the cylindrical shank, those can be fixed here, and these are the, as you can see that this is a straight drill, straight shank drill. This can be placed here, and then you can tighten that so that it actually stays here. So, of course, this is probably the not the and this can actually stay. So, this way it will go to the drill chuck, and then it will be drilled. Now, it can be opened as you loosen it, and it can come out very easily. So, as you can see that this is a cylindrical shank, it is not the taper shank. So, therefore, it will be just placed like that and tightened. So, if you remember your mechanical pencils, so mechanical pencils have the same mechanism here. So, therefore, very often these are called the collet chucks as well. So, these chucks are very popularly used when particularly the diameter of the tool or the diameter of the shank and the tool is less. Okay. So, for small diameter of the drills, normally the such kind of drill chucks are used. So, these are keyless, you do not need a key, and they have the collets. So, those collets, like as I said in the mechanical pencil, remember. Well, here we have a vernier height gauge, and the vernier height gauge, the name itself says that it can measure the height from a particular surface, all right, up to a certain level. Well, so this is movable, this jaw is movable along with this. So, here also, like a vernier scale, you have a main scale and the vernier scale, and depending on the distance that you are measuring, you can find out the reading in the main scale, and the decimals can be found out from the vernier scale according to the principle that we will be discussing in the measurement course in the lectures. Okay. So, this way you can find out different heights with the help of the vernier height gauge. All right. So, this I have already told you that this is the lathe dog or the lathe carrier. So, this is used to impart the rotation when the shaft is located between the centers. All right. So, they are located between the centers. This is fitted in the three jaw chuck or the jaw chuck, and then it will impart the rotation with the help of the by clamping the shaft with the help of this nut. Here we have the three jaw chuck, and these chucks are normally self centering. So, in this there is only one square hole. You can see that this can be rotated, and once this is rotated, all of them, all these jaws will be together coming towards the center, in the sense that this can be tightened. So, if you put any cylindrical shaft here and rotate only this, then all these jaws will be coming together. Of course, there are, for the convenience, there are other holders also, but effectively both have the same function. Like either this or this, you can use an Allen key. All right, you can use an Allen key like this, for example, and if you rotate, so you can see that by rotating this here, all these jaws will be, will show that in the machine also. These jaws will be coming closer. All right. So, either you can tighten a smaller diameter shaft, or you can tighten a bigger diameter shaft. So, depending on the range given here, so different machines will have different ranges from the smaller diameter to the range between the smaller and the bigger diameter. There is a maximum and the minimum diameter. So, this is therefore called the self-centering, meaning that always you can ensure that the shaft that you are mounting, the axis of that shaft will be coaxial with the axis of the spindle or axis of the 3-jaw chuck. So, this is the self-centering chuck, okay, and these are the jaws. Okay. Each of these jaws look like this, and on the other side you can see that this is a rack, and here we have the groove. So, with the help of the jaw, these teeth like in the rack, okay, and with the help of these grooves, it actually moves to and fro along these grooves, all right. So, to hold the bigger diameter or the lesser diameter of the cylinders. Now, that if that was a 3-jaw chuck, you can see that this chuck, also a jaw chuck, it has a 4-jaw chuck, all right. And the 4-jaw chuck is used when the object is not rotational, like not like a shaft, not like a cylindrical job, for example. Here the job is, as you can see, a square type, for example. So, if you have to clamp the square type or non-rotational part, then the 3-jaw chuck is not convenient, because it will not be self-centering, all right. Here each of these jaws can be individually moved, all right. So, again for each of the jaws, as you can see, there is a screw here. So, take the Allen key, put it in this screw hole, and if you rotate, then it will be either moving towards the center, one of them, or moving away from the center, all right. So, similarly you can see that there is another one which is for this jaw, and there is another one for this jaw, and so on. So, for 4 of these jaws we have the individual the screws for moving the jaws independently, okay, for clamping the non-rotational jobs like square, prismatic, for example, all right. Here there is another example, you can see that this is also a 4-jaw chuck, and these are the jaws like this. Jaws are the same type, all right, but here it is individually rotated. As you can see that for each of these jaws we have a square, and each jaw will be rotated individually. Okay, so we have seen here, that is the lathe dog, and here if you see, that is the serving almost the same purpose. This is called the dog plate with the dead center. Here we have the dead center, all right, and this is the dog plate which serves, or the mechanism is similar to the one that we have seen. I have shown it to you earlier. Well, some of the tool holders we are having here. See, for example, this is the tool holder, one tool holder that is used in the turning lathe that you have seen this, okay. And this is an adjustable one that you can adjust actually, and you can with this square thread you can clamp the tool, and while clamping the tool, to maintain the height you have different kind of shims, all right. So, by changing them you can have different height, this height from the center, from the bed surface. So, these are also the tool holders. For small tools, tool can be held here, and this is another one where the tool can be held, and the for tightening, this is the way that you are tightening that. So, the tool will be tightened. So, this is also a tool holder. So, there are different kind of tool holders, as you can see, depending on the tool size, depending on the tool type, you can have different kind of tool holders. Now, these two, one is the follower rest One is the steady rest, this is a steady rest, this is a follower rest. So, these are used when the workpiece length, cylindrical workpiece length is very big. Okay. So, if those two cylindrical, if those type of jobs, if they are held between the centers, it is so lengthy that even then their stiffness cannot be maintained. So, to maintain that in between, we will show it there in the machine. In between the centers, okay, there are these kind of rests which are used. Now, there are certain examples where the job may not be between the centers, but from one center, and then at the other side one of these rests can be used. Okay. That will show you in the machine itself. So, just now I told you about the rests, that is follower rest and the steady rest. Here are the examples. This is also a lathe machine, and here also you can see that a cylindrical job is mounted, and the cylindrical job, this is solid, this is very lengthy, and this is not connected to the dead end, or sorry, dead center. So, in here this job is only mounted on the 3-jaw chuck. So, therefore, if suppose you turn from this side, there will be a lot of bending, because the bending moment will be very high, since this length is very big. So, therefore, there is a steady rest which is required to hold it here, so that the rigidity of this shaft can be maintained, and whenever the machining takes place, the rigidity of the part or the cylindrical job is enough to withstand the force and not getting bended. We have just shown it to you, steady rest to you, where the rest is not moving. Okay. It is supporting the shaft, but it is not moving along with the tool. So, there what happens is that as you remember, that it can have some disturbance of the tool movement. So, this is not this does not happen in the case of the follower rest, and this is also a turning machine, where you have a very lengthy job mounted between the centers, that is between the 3-jaw chuck and the center. This is the revolving center, all right. And since it is very lengthy, so therefore, there is a rest. So, now if you put a steady rest here, in that case the passage will be restricted and the job cannot be turned along the full length of this shaft. So, therefore, this kind of follower rests are used, which will actually move along with the tool. As you can see that as the feed is given to the tool, the follower rest is moving along with the tool. So, therefore, there is no restriction of the tool turning the shaft along the full length of the workpiece, which is not there in case of the steady rest. That is the difference between the steady rest and the follower rest. Once again, steady rest does not move along with the tool post, along with the tool, but the follower rest moves along with the tool, so that there is no disturbance in the process, in the turning. Thank you for your attention.